lecture seminar series. Today is my great pleasure to introduce our speaker, Julia Greer from Caltech. Julia received a bachelor degree in chemical engineering from MIT, followed by a PhD in material science from Stanford University. And also I have to mention that during her time at MIT, she had a minor in advanced music performance. And I'll come back to that later at the end of the introduction. Yeah. And she was for a little bit at Intel, as well as PARC, which is the Palo Alto Research Center. And then after that, she joined the faculty of Caltech in 2007, when she's been ever since. And now currently is the Rubin and Donna Mettler Professor of Material Science, Mechanics, and Medical Engineering. Her research is in the area of mechanics of materials, material science, and specifically nanomechanics and also mechanics of architected media, architected solids, and that's what she's going to talk about today. In addition to her faculty career, she's also the Fletcher Foundation Director of the Kavli Nanoscience Institute, as well as the Editor-in-Chief of the Journal of Applied Physics. Her list of awards, accolades, distinctions is very long, so I'm not going to use up that time to list them all. I'm just going to mention a couple. Very recently, she was awarded a Dye Medal from the ASME, as well as the Erringen Medal from the SES, the Society of Engineering and Science, that many of us in this room are familiar with. She was also named a Vannevar Bush Faculty Fellow from the Department of Defense, and then she has a number of career awards from NSF, DOE, DARPA, you name it. Last but not least, I want to mention that also her work is prominently featured also in popular mechanics venues as well as in the media. And I'd like to conclude with this note, which I know is very dear to her heart. In addition to being a very accomplished scientist, she's also a pianist, and she's performed widely, both as a soloist and as well as in with the chamber ensembles in the Southern California area. So please join me in welcoming Julia Greer, and the floor is yours.
Thank you. Oh my God. Is this on? Okay, awesome. All right, so every colorful domain here represents a type of material, a category of materials that we know how to make today. And so the picture that emerges right away is that we're very good at making materials that are simultaneously strong and heavy or lightweight and weak, right? And so what we're not yet so good at is getting into the so-called white space, where materials can be simultaneously mechanically resilient and lightweight. Now, this is a log-log plot, so even a small increment within the space already represents a substantial change. So the question was, this is 10 years ago, how do we get into this white space if everything we know how to make today is already plotted here? So the way we thought of it is by applying this concept of architecture to materials design. So if you look at the largest man-made stone monument, right, this is the Great Pyramid of Giza, it stands 150 meters tall, it weighs 6 million tons, and certainly not a very elegant structure, I would say, right? So then, in contrast to the Eiffel Tower, which stands twice as tall, and it weighs 3 orders of magnitude less. And as far as I know, they're both still standing, right? So what that tells us is that by properly architecting your structure, you can actually get away with using a lot less material without any sacrifice in the mechanical strength. So when we first began this research, we were collaborating with HRL, and we made an entirely nickel microlattice. So what you're looking at is the world's most normal dandelion. There's nothing photoshopped here. There's nothing unusual here, just a normal dandelion in Malibu. And this nickel microlattice is sitting on top of it, hardly perturbing it at all. In fact, if you were to hold the microlattice in one hand and a feather in the other, and to release them at the same time, the feather would fall down faster. So they're very, very lightweight. But to get to the simultaneous attainment of the strength and the lightweight, you have to go down 3 more orders of magnitude in the dimensional reduction. So all of these black and white images you're looking at here were at some point made by students in my group, and they're black and white because these are scanning electron microscope images. You can see that there's an obvious level of porosity, and that is that they're all cellular solids, right? There's a less obvious level of porosity, and that is that the nanoscale building blocks that comprise them can be made hollow. And so the wall thickness here can be on the order of 10 nanometers or so. So the largest dimension in this entire solid that looks like a solid cloud sitting on your hand is only 10 nanometers. So it's 99.9% error. Those of you who are fans of Doctor Who, here's a microtardus. It's about 1/1000th of your hair diameter. It's very small. We're not limited to periodicity. We can make very sophisticated structures, and I'll tell you a lot about this later. But basically, this is possibly the way, right? Architecting and maybe combining these nanometer type length scales with the size effect. So what we're creating is ultimately not really a structure and not really a material, it's both. And so this is why we felt it was appropriate to call them structural metamaterials. Now, hopefully I've convinced you that these are very lightweight, but I have yet to show you that they are in fact strong and mechanically resilient. So this is something we and many other groups actually demonstrated a while back, and that is that if you were to plot the strength as a function of size for some very common metals like gold and silver and copper, and in their single crystalline form. So that doesn't mean that they're defect-free, that just means that they don't have any grain boundaries. So what we observed is this ubiquitous smaller, stronger size effect. This is, again, a power law type strengthening. And so what that means is that if you take something very malleable like copper and reduce its dimensions to about 200 nanometers, it becomes as strong as steel. So smaller, stronger size effect. Okay. Now, take exactly the same metals and deposit them using a different technique, for example, a thin film type deposition, and all of a sudden, this effect is reversed. And smaller is now weaker. Now, this is a more modest size effect. It's no longer on the log-log plot, but it's non-negligent. So it turns out that strength is not a constant, like maybe some of you are learning in classes, but it's dependent on size when you get down to these nanometer length scales, like the architectures we were describing before. Now, here's another example of a size effect. This is a glass rod that's about 150 nanometers in diameter. And we're pulling on it at room temperature. And watch what happens. It's glass, room temperature, not hot. So we're deforming it, it's forming a neck, and it deforms by about 100% strain prior to failure. So glasses are not supposed to do that. I don't know about you, but anyone who's really tried to do this, maybe with a piece of chalk, this is not supposed to happen, right? And here's the last example I want to show you. This is a titanium nitride single unit cell of one of those nano-architectures. Very, very brittle ceramic. So this beam is bending. It's a ceramic beam, and it's bending under global compression. So if you were to calculate the mesis stress and then to calculate the tensile component, it's something like 1.7 GPa. Ceramics are not supposed to stay intact when you apply 1.7 GPa of tension, uniaxial tension to them. Yeah, this one is doing it over multiple cycles. And it'll keep doing this, I promise you. So the takeaway message here is this. Sometimes materials can get stronger. Sometimes they get weaker. Some other times you can suppress brittle failure. But all of these effects emerge only at the nanoscale. So the big question to us, to ourselves about a decade ago was, can we somehow harness all of these beneficial size effects and proliferate them onto the larger scales? And this is where the architecture comes into play. Can we combine these two phenomena into creating an entirely new, maybe, class of materials? So I want to spend a few words describing on how we make them. So this is a technique called two-photon lithography. I have a question for all of you. Do you have an instrument called the nanoscribe here?
No, but we know.
You know what it is.
Many of us know what it is.
Okay, I highly recommend it. So this is, okay, so this instrument is called there's this company, Nanoscribe, that makes it. It's a two-photon lithography instrument, and the way it works is that it's an IR laser, and so in a single voxel it releases exactly 2 photons. And so this is how you can bring down the resolution to submicron and have a sufficient amount of power to cross-link the photosensitive resin within that voxel. Now that voxel is rastered in space, in 3-dimensional space, and as it's traveling in space, it's cross-linking whatever shape it's trying to make. So we can write a nano version of each one of you. Complexity comes for free. So there's no mask, there's no periodicity, and that's how we were able to make all of, like the micro-TARDIS, for example, right? So this is the speed at which it writes. So how many of you think that this is fast? How many of you think that this is slow? Okay, and the rest of you are just like, none. not convinced. That's okay. So it depends, you're right. So basically, this is great for lab research, but it's not great for manufacturability. So if you wanted to make an entire world nano-architected, which is what I want to do, we can't really use the nanoscribe for that. So for that, you have to figure out a way to expose maybe an entire sample or an entire field in a single laser exposure instead of a single voxel. And so for that, we developed a different technique, and that utilizes a metasurface mask. So these are little silicon pillars, nanopillars, on a mask. What ends up happening is that when you shine a different kind of laser, this is a green laser, it creates a pattern of standing waves like so. And so all of these high intensity points also provide a sufficient amount of power for a different photosensitive resin to cross-link, but the entire field can then be cross-linked in a single laser exposure. And so what ends up happening is that you have, for us, this is very big. It's an inch by an inch sheet of paper, effectively. And then when you look in the cross-section, you can see it's fully nano-architected. So this is one way for how we can actually scale this up and make this into production of sheets. So that's another technique that we use. And then we also, of course, are very versatile in terms of the 3D printing capabilities. In fact, my mischievous grad students made some very poisonous gummy bears. And so I had to put like big boundaries everywhere saying, please don't eat these, because they're very, very poisonous, but very realistic looking. Okay, so most of the samples we'll work with are kind of nano or micro scale, and so we're not able to see them in any kind of an optical technique. So this is a scanning electron microscope that is equipped with a nano-mechanical module that is capable of perturbing them in various mechanical and electrochemical ways at different temperatures. And these are different inquisition devices. So these are the kinds of grips that we make ourselves out of diamond. And what that enables us to do is to pull on things that are maybe 100 nanometers to 200 nanometers in diameter, as well as to perturb things that are many hundreds of microns in diameter. So there's a multitude of scales that we can probe. Okay, so now that I told you how we make our samples and the hypothesis that we're trying to probe, here's the big experiment. This is my former student, Lucas Meza, who was first to do this experiment. This is an octet nanolattice. An octet just is a type of cellular solid that is stretching dominated, so it's supposed to be the stiffest of the classification. The wall thickness here is about 50 nanometers, so very small. It's about 99% dense. Now, how many of you know what atomic layer deposition is? ALD. Okay, all right. So in the ALD community, you know, they'll tell you, we can deposit anything you want as long as it's alumina. So here's alumina, very brittle ceramic, ALD deposit. It's hollow on the inside. And so it's basically like your coffee mug with a severe case of osteoporosis. And so when we compress it, of course, we're expecting nothing more than for it to crush and die and to shatter, and nothing interesting happens, basically, right? So that's exactly what we observed. A little bit disappointing, but we predicted this, right? So crushed and died. So now let's repeat this experiment. And the only thing that we're going to do differently is we're going to reduce the wall thickness by a factor of 5. So instead of 50 nanometers, we're going to go down to 10 nanometers. Same alumina, amorphous, no dislocations, no grain boundaries, nothing of the sort. And we're going to compress it so it's should be even more susceptible to failure, right? So now we're compressing it. It's very, very brittle. It's very ceramic. It's very open. And what is happening is that we're compressing it to about almost to 50% in this one. And this particular ceramic thinks of itself as a sponge, so it fully recovers. So if that doesn't convince you that there is, in fact, a size effect, I'm just going to fly back to California right now. So this was a big finding for us. We hadn't expected for this to happen. And so now that we saw this, I would like to show you all the things we've learned in the last 10 years since that very first set of experiments. So the first thing we learned is that the nanolattices don't have to be periodic. In fact, they shouldn't even be called nanolattices. These nano-architected materials were made by my former student, Carlos Portela, who developed these nano-labyrinthine alumina architectures that are all shell-based. There are no beams. There are no beams, there are no nodes. And you can see that every time there's a hysteretic type of behavior, there's a lot of energy dissipation that's occurring, and there's always full recoverability, right? The second thing we learned was that the structure doesn't have to have homogeneous density. In fact, you can incorporate different regions. In fact, this bottom part is more compliant, so it's fully densifying before the top part is even aware that it's being compressed. You can also see that reflected in the stress strain data. So now we can build in trajectories of deformation or even failure. This is something new to us, is studying fracture in these nano-architected materials. But we now understand how we can pre-design the trajectories into these materials. It turns out they're also very good for breakdown, for controlling breakdown voltage and supercapacitors. So there's multifunctionality that comes with these mechanical types of materials. This is a hierarchical nanolattice. So each individual beam is now comprised of self-similar unit cells. And now what you're observing as you're compressing it is that there's kinking that's occurring in the lowest degree of hierarchy. And so we're really expecting it to shatter right here. So for catastrophic failure to initiate at this stress concentration, and it fully recovers. So what we're learning is that hollow, brittle nanoarchitectures recover under complex stress states, in complex shapes, and under every kind of deformation. So this is not unique to periodicity. This is not unique to any kind of lattice behavior. Rather, it's a function of the combined size effect with the nano-architecting type of an approach. Okay, so that hollow, this is very important, actually. They're all hollow architectures. So I imagine that most of you have mechanics background. So we, of course, try to understand why this happened. This is very unusual behavior, right? So there's an elastic instability called shell buckling that could be the root cause of this, right? Like that could be causing this. So as we're compressing a hollow beam-based architecture, maybe the reason why it's able to spring back is because it's experiencing buckling. Okay, so there's this type of a criterion that we can set for failure. So if we set up the criterion for local buckling and that it set it equal to yielding, which for a brittle material should just be its fracture strength, there's this T, which is the thickness of the hollow beam, and the A, radius of the hollow beam. There's this ratio, T over A, that can be calculated. And so this critical ratio, what that implies is that if the ratio is higher than that, your material will fail prior to buckling. And if it's lower than that, then you should experience a structural response where you see buckling. So let's see what happens here. So this is what mechanics tells us, right? So it turns out that for the 10 nanometer wall thick nano architecture, which you saw, the octet, the deformation, that ratio is 0.016, so that's below 0.03. So it makes sense that it recovers. And so you can see in the data, these are different unit cell sizes, these are different relative densities, actually, and you can see it recovers every time, and the sample looks very similar to before and after deformation. And as we increase the wall thickness in first approach and then supersede that critical thickness, you see the deformation becomes a lot more catastrophic, a lot more jerky, and this last one just basically dies in a single burst. So, seems like the answer lies in mechanics. Mechanics tells us everything, so this is really great. And so what that means is that if we were to build a building that's 10 centimeters thick, right, and then has 3-meter diameter tubes that are made out of concrete, and then we construct it into a giant building, and then a giant comes and steps on it, then the whole building will spring just like our nanolattices will spring right back, right? That's what mechanics tells us. As long as T over A is scale-free, T over A is continuous. It should work across scales, right? Okay, well, good that you're smiling. Of course, this will never happen. So who knows why? A student, please. Where is the size effect here? How does the size effect manifest itself here that this would never happen in a building with the same T over A ratio, but it happens in the nano-architected material? Well, so it begins with an F and ends with laws. So brittle materials fail at flaws, right? So first of all, the probability of finding a very broad distribution of flaws in something that's 10 centimeters thick is 100%. And so no matter what, the local stresses ahead of all of these microvoids and inclusions will always exceed the material fracture strength. So before this structure even gets a chance to experience any kind of structural response, your material will locally fail. In contrast to something that's only 10 nanometers thick, first of all, the probability of finding a flaw is much lower, and the size of the largest flaw is only 10 nanometers. So the size effect manifests itself here in our ability to make much closer to ideal materials. So if we were to fill up this room with something like concrete, it won't be as high integrity of a material than the same volume made with nano-architected structures out of the same solid constituent. Okay, all right, so it's all about the defects. This is also very important. Okay, so the natural question after that was, okay, so since we observed that the hollow, brittle building blocks always recover, what happens in the monolithic ones? So of course carbon seems to be a good material for that. So this is now monolithic, right? So fully dense carbon. This is a carbon micropillar, and we're going to compress it. So you've all written with pencils before, right? So this is effectively pushing really hard on a pencil. So here we are, compressing a carbon micropillar. And as we're compressing it, you can see the stress scale here. So we're almost at 4 GPa, 4 gigapascals compressive stress on carbon. And it's certainly not enjoying itself, but it's not fracturing, right? It's bending, it's barreling, it's doing a lot of things. We're up to 7 gigapascals, and it's not fracturing. That's unusual, right? Like, so this carbon thinks of itself as rubber. Okay, so the first thing we had to do was explain why this happens. So when we looked closely at the microstructure of this carbon, we identified multiple curved sp2 hybridized fragments that are graphene-like. And so upon the global application of axial, uniaxial stress or strain, they're able to transform in these shear transformation zones that are distributed throughout the pillar so that prior to any kind of failure, they're able to accommodate all of the axial stress through the shear transformations. And these local shear transformations don't coalesce to brittle failure or to any kind of failure for a pretty substantial amount of deformation. So to confirm this hypothesis, we collaborated with a group at Tsinghua University. So this is Xiaoyan Li's group that was able to reproduce that very same microstructure in their MD simulations. And then, of course, my former advisor always presents this challenge to me, Bill Nix. He says, don't believe anybody who tells you about ductility and compression. You can make anything ductile in compression. So here's some tensile data. Hopefully I can convince you. This is real data, this one. So these are our carbon micropillars that very clearly show ductility up to about 20% each time at room temperature, so it's real. And so it turns out that our theory, or our hypothesis anyway, was in fact true. There are these small shear transformation zones, and you can see where the strain is localized into these. And in fact, it's localized to a very high strain prior to failure, and only then failure occurs only once they coalesce and form a percolating path through the entire sample. So here we are. We made nanoscale building blocks that are fully recoverable. We know why they recover. This is going to work great. Carbon is cheap, carbon is stiff, carbon is great. So we're going to go architect, right? March forward and architect with these. So here's what happened when we architected with carbon. Bad news happened. We learned that no matter what you make out of carbon, this is an iso truss, this is an octet truss, different relative densities. Every single time they fail, just like you would expect for a brittle material. So the defects, the structural defects, override everything here. So what we learned, again, smacked on our faces, was that the importance of defects can be underestimated. So basically, every single time, the stress concentration at every junction was the cause of failure for the entire structure. Having said that, right, so I want everyone to appreciate this. So brittle materials that are hollow always recover. Brittle materials that are monolithic never do. So no matter what you make out of this, at least in our experience. I want to bring everybody back to the white space structure, parameter space that I showed. So where this is what I showed you before, and it looks like by just nano-architecting, we are in fact able to get into the white space. And this is a long time ago, so now hopefully many of you can do better. We can do better than we used to. So this is clearly a pathway to get into the white space, right? This combination, this architecting with all kinds of nanoscale building blocks. We also learned that you can make your material look good depending on what you decide to plot. So for example, specific tensile strength, we're showing that we're better, we can outperform balsa wood, for example. So these materials can always be made to look better than everything else. And so you just have to find the right parameter. And so speaking of this, I want to redeem the carbon a little bit. So it turns out that the carbon points, which are right here, even though it failed every single time, it's the only material that approaches the theoretical limit. So these are all the nanolattices, and they're all, of course, in the lower density regime. They're pretty far off from the theoretical limit. We can also talk about how do you define the theoretical limit for something at the nanoscale, and we can definitely have a discussion about this, and that's why we put a ribbon here, because diamond and graphene are fundamentally very different carbon structures. But nevertheless, the carbon is the only material in the high density regime that can get to the theoretical strength, so that's encouraging. And also, I just wanted to redeem carbon a little more. So it turns out that we just maybe weren't doing the right experiment on the carbon. So up to this point, everything I showed you was quasi-static deformation. So my former student, Carlos, who is a professor at MIT, now utilized this technique called LIPIT, laser-induced particle impact test, where he effectively shot microprojectiles at the carbon nanolattices and learned about their high-impact behavior. So don't blink when I show you the movie. So these are some of the nanolattices. So these are not carbon nanopillars. These are carbon nanolattices. So now each individual block is kind of like one of those rubber nanopillars. Now watch, the unit cell size here is something like 2 microns, so it's very, very small. There's a separation of scales. The projectiles are something like 30 microns in diameter. And the idea is that the projectile is being launched at the lattice, and we're going to watch it happen, so don't blink. So here it comes. Did you see it? Okay. All right. So what Carlos learned is that there were 3 different types of deformation. So the first one was just the elastic rebound. So basically the projectile went somewhere and we didn't see much. The second was capturing the projectile, so it would get embedded into the nanolattice. And the third one was the combination of the two, where we had the permanent crater mark, and then the projectile bounced. We never observed any penetration of the projectile to the underlying material up to the speeds of almost 1 kilometer per second. So it turns out that they're pretty good at impact mitigation. And in fact, when we plotted the rebound energy as a function of impact energy, we can see a big variation with the relative density. So this is 23%, this is 14%. And you can see that for these samples, we're getting pretty close to ideal impact mitigation. And when we compare our data, so this is the red points is all the data that Carlos collected with some of the Kevlar in typical materials that would be used for impact mitigation, you can see that it holds its own pretty well and pretty promising in terms of shielding impact. So we just weren't doing the right test on the carbon. So that's yet another learning here. Okay. Right. Now, I mentioned a few times the importance of the nodes, and that basically nodes are kind of bad news. And I want to really show this to you in our tensile experiment. So here's a notched nano-architected material, and we're pulling on it. And as we're pulling on it, it fractures in a direction orthogonal to the load. And we learned that no matter which way you orient the initial notch, it will always fail this way, and it'll always fail along the nodal plane. So you can see that each node contains a small crack, maybe, or maybe two. And they're certainly deformed and distorted in those locations. This happens in compression as well. The first cycle always looks different from the second through nth. And so basically in the first cycle, we pre-damage the architecture where the nodes concentrate all the damage. And so it doesn't preclude recoverability, but it certainly deteriorates the strength. So nodes are bad news. Structural defects in general are bad news. So my former student, Weedy, decided to completely do away with the nodes, and he created these woven architectures. So now you can note that each individual beam is comprised of 3 individual strands that are not touching each other. So it's like a DNA molecule, but with 3 strands. Okay? So now watch, he actually made a nanolattice out of this. You can see there's not a single junction. There's not a single junction where the beams come in contact with one another. So now I'm going to show you the deformation of the woven nanolattice on the left and the monolithic nanolattice on the right. You can see this one fractures right away along the nodal plane, and the one on the left never fractures. And the benefit of using this instrument is that we now can conduct the compression and tension on the same sample. Here we had to kill another nanolattice. But this one is the same sample that was tensed first, and now it's being compressed. And you can see how much extensibility in both directions we can get out of these woven nano-architectures. And when we plot the strain to failure, you can see how far you can push the limit of deformability of these materials. They're very compliant, but they're extremely resilient to any kind of breakage. So this is one way of how one might avoid using nodes in their architectures. Now, what's interesting is to understand the mechanics of this, because now instead of the relative density being a very simple function of the slenderness ratio, effectively, of your beams, now we have the effective radius, right? Now we have the small r star, which is the strand radius, and then the capital R star, which is the effective beam diameter. And then what we can do from this, what Weedy did, is he actually plotted the entire parameter space on the axial stiffness and the bending stiffness, which can be entirely controlled by these 2 distinct slenderness ratios, the effective one and the real one. And what's really nice about this is that if you were to think about applications of, say, microneedles that are penetrating your skin, like, for example, for drug delivery or for patches, you can tune the axial stiffness of these while having the drug being released from every surface of the triple strand or something like that, right? So now what you can do is decouple the functionality from the mechanics and fully tune the mechanics to fit your end application. So this is something that we are very much working towards now. Okay, but Weedy didn't stop here. This was his COVID project. And so Weedy has a friend, Max Saccone, who is now a professor at CU Boulder, who is big into rock climbing. And so Weedy said, well, okay, there are a lot of knots that are involved in climbing. And so why not make a knotted nanolattice, right? So it turns out that this is actually a fascinating problem, has been a fascinating problem for mathematicians for a long time, understanding the mathematics and the mechanics of the knots. So let me walk you through. So here's a woven nanoarchitecture where a single strand starts at the top and ends at the bottom just by this trajectory, just following this kind of a trajectory through the unit cell. In a knotted architecture, you also have a single strand that starts at the top and ends at the bottom, but it makes a loop before it gets to the bottom, right? So when you pull on it, what do you think is going to happen here? It's going to unbend first, right? Like it's going to straighten out, and then you're going to pull on the strand, and then we'll see what happens. Here, you're going to first unbend as well. But after that, what's going to happen? Hopefully, you're going to start tying the knot. Yeah. So so we had never done this before, so we just did this last year. So knotted on the left, woven on the right. So here we are. Here's the single strand that subtends all the way. So watch what happens. So first they start off together, right? Because we're first uncoiling. And then the one that's woven shifts entirely into the stretching regime, whereas this one shifts entirely into friction-dominated regime because now we're tying the knot, and the slope change indicates the work of friction that's occurring while we're tying this knot prior to failure. Look at this, it's 1,500% strain. So what we uncovered is an entirely new mechanism of energy dissipation that's available to nano-architected materials that we had never seen before. So this entire thing is the work of friction by tying the knot. So this was kind of a fun little project. Right. So then it turns out that Pedro Rice actually did all this theory for us a long time ago. So if you look at the knot geometry, depending on how many times it interwaves, there are actually several parameters that feed into this. We can figure out, in fact, we can gain some insights into the friction at the nanoscale. Because I would conjecture that friction at the nanoscale needs to be thought of differently from how we think of it in bulk. Because now we have surface stresses. We have terminated chemical bonds. We have all kinds of functionalities and surface treatments like UV treatment or something like that that plays into that. And now these forces become comparable to one another. And so this is something that's worth studying, in my opinion. So everything that's in red is something that we can measure in our experiment, and everything that's in purple is something that's a function of geometry or material or how we designed it. So we have the knowledge of that as well. And so when we do this experiment, what we was able to show are these contours of the product of the coefficient of friction, the mu here, and the elastic modulus of the material. And so there are these contours that show you that it's really their product that determines the load versus displacement, which we converted into strain response. And he even had some experimental data to show that the different surface treatment, which would give a different coefficient of friction, for example, with UV light, already shows this shift towards the theoretically predicted behavior. So this was kind of a neat way for us to study friction. So if anybody is interested in friction at the nanoscale, this would be, I'd like to offer this as a useful way to do it. Okay. Now, of course, everybody's doing AI right now, so I just wanted to show you a little bit on our collaborative work with Dennis Kochman's group that uses the forward and the inverse model to predict stiffness, three-dimensional anisotropic stiffness of something that looks very complex. So this is actually trabecular bone. This is a real sample of trabecular bone based on micro-CT, and this is the predicted architecture based on AI. And what my student, my former student Wei Ting, was able to demonstrate is that when you take this AM-generated model and then make a sample out of it, it looks very isotropic, right? You wouldn't, by looking at this, there's no way you would be able to know whether it's isotropic or anisotropic, but you certainly would never be able to infer what the stiffness is. And so Dennis's group predicted that this would be the stiffness surface, and then these points are the ones that we measured experimentally. And so these are the data that you see here, and sure enough, in the three orthogonal directions, you can very clearly see the stiffness increasing. So now you can design very complex architectures that are entirely unpredictable using any kind of theory or even FEM simulations using this kind of AI-based design. So this was kind of a neat finding. Okay, I'm going to shift gears, and I'd like to ask if anyone has any questions right now, because I'm going to switch to a little more towards additive manufacturing. So this was kind of more mechanics heavy. So welcome.
When are you going to explain how you're going to scale this up?
I did. I showed you my interference lithography. I know. It's really hard. It's really hard.
I want that building that you showed.
I do too. Actually, my students say to put the airplane on a shelf. I don't know where that came from. Said you used it in one of your TED Talks. Why would you want an airplane on the shelf? I don't know, but that's the idea, right? Like, so we can make things that you can just easily pick up and put them. Yeah, that's it's a big problem. Scaling up is a big problem.
Can you briefly describe how you make that three-stranded wire?
Yeah, so it's the nanoscribe. It's that instrument. It's not very easy, but if you know what you're doing, you can make it. So it's not something that will require, like a PhD student can learn it in a couple of months. Yeah. You really do need the nanoscribe, though. There's no 3D printer, there's no other instrument that we've been able to convince to make something like that, but because they would be touching. Our main problem was how do you make sure that they don't have contact initially? That's hard, because you have some diffusion during polymerization. Yeah, but the nanoscribe should be able to do it. When you make them out of superconductors or semiconductors, probably, right? So we haven't really studied this, but the kinds of materials we've worked with so far don't really have a band gap. They're not. That would be in the semiconductor world. So if we were to go in that direction, I would expect some coupling, yeah. We're not quite at that scale yet and not quite in that material space yet. Yeah, thank you for asking. Okay, any more mechanics questions? Well, oh, thank you.
This just love actually for all the experiments you showed was actually assuming homogeneous deformation.
Yes, so that's a great question. It's not local stresses and strains. We want to think of these as materials. So it's of course the homogenized global stress and strain because we treat them as a material. And if you would have to do pretty sophisticated either MD simulations, which have unrealistic strain rates and don't really account for the global structure, or continuum simulations, which don't really account for any kind of atomistic variations or defects. So either way you look at it, there's really no better way that I can think of right now to represent the holistic picture, so we think of them as materials for now. Yeah, okay. So okay, that's a great question. So it's not fair, it wasn't measured on the nanoscale, and so it's not a fair comparison. And so what we're doing now is we're making composites with these nano-architected sheets, and then we'll compare them to the very same dimensions of Kevlar samples, and that's a much more fair comparison. That was the first demonstration of any kind of impact on the nano-architected layers, and so at that point it made sense to compare them, but at the different length scales, but it's not fair, and you're absolutely right, yeah. Yeah. Thank you. Okay, so in the interest of time, I'm going to move on. How many of you are polymer chemists or know anything about polymer chemistry? Yes. Great. So the rest of you, please just bear with me. It's going to be a little bit of chemistry. So when you work with a nanoscribe or with any kind of a 3D printer, typically you would go to some manufacturer to buy your resins, right? And that's actually how they get you because they charge a lot of money for it. So if you have very clever Caltech students, you can start synthesizing your own resins. And we've been very interested in hydrogel-driven synthesis because it's not toxic, it's much more sustainable, it's better for the environment in every way. So this right here is PEGDA. It's polyethylene glycol. It's a hydrogel. And this whole cocktail represents all the necessary chemistry to initiate a free radical polymerization. And so when you start with this cocktail in its liquid form, and you initiate this, that's how you 3D print effectively, right? So you cross-link the polymer under the effect of that particular light. So this is a UV 3D printer. This is not nanoscribe, this is UV light. So what my former student Max did is he said, well, we can actually develop this additive manufacturing process in a way that involves pretty much some hydrogels and metal salts. So when you start, we first 3D prints is this organogel, so that's this cocktail right here. Then he exchanges the solvent with water, and so this just becomes a blank hydrogel, and then he infuses it with metal salts. So this could be silver nitrate, copper nitrate, et cetera. So just some regular metal salts, nothing sophisticated here. He then subjects it to a two-step thermal treatment. In one of them, it's called calcination. So we basically burn off all the organic content to produce a metal oxide. And in the second step, we reduce it to the parent metal. Everything you see here is a schematic, okay? Everything you see on the next slide is a real image. So it's a very pretty project. So you can see that we begin with organogel. Here's a hydrogel, turns into clear. And then the turquoise copper nitrate salt is the typical color for that. Then the copper oxide, this is a solid now, no, not a hydrogel anymore. This is a rigid solid copper oxide, and then it turns into a copper metal. And Max was pushed to demonstrate this process, which we coined hydrogel infusion additive manufacturing, or HIAM, for a variety of different metals. And what we're observing is that you can, of course, have metals of a single composition. But what's much more powerful is that we can make metal alloys, and we can make high entropy alloys, and we can make alloys that are very hard to form, for example, tungsten. So what this enables us to do is a massively parallel experimental approach where you can make a lot of hydrogel blanks and then infuse them with different salts and then create kinetically driven, in addition to thermodynamically driven microstructures. And one consequence of this was that we end up with some very weird microstructures. So this is an EBSD map, which shows you the different colors correspond to different crystallographic orientation of the grains. Here's the pole figure. So this is copper. What we're observing is that it forms a lot of annealing twins. So this microstructure is very twinned, very heavily twinned. It's polycrystalline. It doesn't have a particular texture. So this is kind of an unusual microstructure. And like I said, there's a lot of kinetic effects, right? Because you're reducing, you're reducing your copper oxide into copper. So there's a lot of oxygen diffusion concomitant with sintering and with grain growth and pore formation and atomic diffusion. So there's a lot happening at the same time. And so what we've learned, is that every time we make any kind of metal using this HIAM process, the strength is elevated pretty substantially. And so even when we correct by the presence of these twin boundaries, we can account for some of the strength enhancement, but not all of it. And so we're not sure why. So what we're observing is that every time we make something, it's stronger than what would be produced using a regular process, but these chemically derived metals have all the normal characteristics like conductivity and microstructure and everything that copper would, but they're just a lot stronger. So there's something to think about for that. Okay, so then the next step, natural step, was can we push this process to the nanoscale, right? So everything I showed you just now was micro. You can touch it with your hand, you can see it. Can we push this to the nanoscale? Because this is where interesting things are. Hopefully I convinced you of that. So my student Wengshen developed this different cocktail for the nanoscribe. So now we're going down to that super fancy 2-photon lithography approach. So what this is kind of, we started with a simple geometry. We decided not to go to the nanolattices right away. She just made a nanopillar, a nickel nanopillar. She's trying to anyway, to make a nickel nanopillar. So here's a nickel infused polymer. So we have the nickel nitrate salt in it. It's mostly hydrogel, and it's very small. And here's the reaction that converts the nickel nitrate to the nickel oxide. And so here's our nickel oxide pillar. We're almost at the finish line, right? We haven't yet reduced it to nickel. It's nickel oxide. And so what we learned is that it's nanocrystalline. It's not amorphous. This is important. So now we know the only job that this pillar has to do is to convert its nickel oxide grains into the nickel grains, and that's it. So what kind of microstructure should we expect in this one nanopillar? We have I just went over kind of all the processes that are accommodating this transformation, right? There's definitely oxygen diffusion. There's pore formation. There's a lot going on. So the candidates are, it could be single crystalline. It's very surface dominated. These pillars are 200 nanometers in diameter, right? Very surface dominated. So we could have just driven out all the grain boundaries from the original nickel oxide grains. Could be single crystalline. Could be nano-twinned because we've seen the twins, right? We've seen the formation of twins. Could be nanocrystalline, pretty likely to be nanocrystalline, in fact, right? Because it's nanocrystalline in its oxide precursor phase. And could also be nanoporous because the oxygen is diffusing away. So there probably, maybe would be some pores. Okay, so I want you to vote. This is not the sad voting that just happened a couple of days ago. This is a much more exciting voting. So how many people think it's, you may vote once and only once, but you have to vote once. So how many people think it's single crystalline? One, thank you. Your team single crystal, all right, awesome. How many people think it's gonna be nano-twinned? Okay, great. Nanocrystalline, team nanocrystalline. Everybody else thinks it's nanoporous? Because you have to vote, okay, all right. Okay, are you ready? I can't flip the thing. It's all of the above. It's actually remarkable. This single nanopillar is so hierarchical and so complex in its tiny little body. Oh, man. So look at this. This is the cross-section in the TEM. This right here is 25 nanometers. So there are grains that are populating the walls, but it's a bamboo-like structure, so it's exactly one grain across, multiple grains stacked on top of one another. There are a lot of pores. There are some single crystalline ligaments that we saw. Here's the nickel wall right here. So you can very clearly see the twins, very clearly see the grain boundaries. And here's some of the satellite peaks in the diffraction pattern that show you the presence of twins. So it's every single one of those microstructures that I just showed you. So what is remarkable about this is that at the bulk scale, this would be considered a very crappy microstructure, right? If you were to make a metal part that had nanocrystals, nanotwins, pores, and everything, it would be thrown away, right? So then, of course, we now need to do some nanomechanical experiments. So we have this approach where we do these experiments in situ so that we can watch the deformation. And we just recently, a couple of years ago, got this amazing instrument called femtotools. So if you don't have that, I highly recommend it. I think it's the only instrument that's able to do true displacement rate control. So it's not an inherently load-controlled instrument like every nanodenter is, but this is, isn't Bill Gerber, wasn't Bill Gerber in this department? Yeah, here's some. So this is not the Hyzotron like Bill Gerber used to use. This is not a nanodetector. This is an entirely new approach, and it's actually a great instrument. So we're doing this in focused ion beam. Here's the setup of the instrument. So we're able to observe the deformation even on something as small as this nanopillar, and we can see the deformation. So 145 nanometers. Do you guys know how small that is? It's very small. So it appears that in this particular sample, it kind of sheared off along a particular shear plane. So we collaborated with Huajin Gao's group on conducting these molecular dynamic simulations, again, putting in the microstructure that we're observing. And so it appears that the molecular dynamic simulations are able to reproduce the deformation that we're observing experimentally. They studied the effect of the presence of one dominant grain boundary versus not having it. And it appears that it's just basically always grain boundary dominated plasticity. So every time we push these pillars past the yield point, they always undergo these grain boundary assisted deformation. But here's the exciting part. I think it's kind of exciting. So when we plot the stress as a function of pillar diameter, and there's quite a bit of literature now on the deformation of nickel specifically, here's what emerges. This is only nickel. There are no other metals that we're comparing. This is that smaller, stronger size effect that I showed you before in single crystalline nickel, right? So single crystalline nanopillars always has this slope, this strengthening slope of 0.6 to 0.7. These are all the nanocrystalline pillars that are always weaker. The nanocrystalline are always weaker than their single crystalline counterparts. And here's our data. And what we're observing is that these very crappy nanopillars that combine every bad defect that you can think of in the metal microstructure are stronger than all the other microstructures of nickel, and they're a lot less susceptible to the size effect. So they don't lose their strength when they become larger. So in the nano world, everything is upside down. The real answer to this, of course, is that we're observing a structural response in a tiny little nanopillar. So because our length scales are so comparable now, the length scale of the defects and the length scale of the sample are so close to one another that our structures are able to redistribute the load much more efficiently instead of catastrophic failure, which is what you would observe in something like that in bulk. So we got structural response out of a 150 nanometer pillar. Okay. All right, and I just have one last topic on soft plasticity. Do we have like 5 minutes? How many people care about soft matter here? Nobody cares about soft. We have to do it very quickly. Okay, so we've been working with a very interesting class of materials called metal polyelectrolyte complexes. And the idea is that you have a metal that's coordinating with a polyanion backbone in a polymer. I'm going to skip through that. So here's the metal cross-linker. And when it cross-links into a gel, it forms, so we can print with it. So the first thing we demonstrate is that we can use metal ions to print with as the cross-linking agent. So there are monovalent metals, divalent metals, and trivalent metals. And so it turns out that there's a big difference in their mechanical response. So when we pull on the aluminum gel, you can see it's very stiff and it's not very stretchy, but a calcium gel, same gel, just with a different metal ion, stretches tremendously. Right? So when we plot this, we're also observing this difference, very big difference between monovalent, divalent, and trivalent. And so it turns out that the way that these are dynamic bonds, so they're forming and reforming. So it turns out that in the divalent case, you see this more of this homogeneous stretching, like in the case of calcium. And in the trivalent case, the way that the metal ion coordinates with the polymer backbone, it forms these clusters. So it makes it stiffer and a lot less stretchy. So when my student Sola looked into the mechanical effects and studied the function, the time dependence of these is very viscoelastic type materials, what she uncovered is that when you plot the strain versus time, there's a crossover point between a divalent metal, like nickel, and a trivalent metal, like aluminum. So here's how it manifests itself. If you make a bilayer strip, here's aluminum and here's nickel. Aluminum is on the left, nickel is on the right. And we're going to compress it at a strain rate of 0.02 per second. Here's what happens. So she's compressing it, and the structure, of course, buckles, right? It's very, very compliant. It's gel. It's a gel. Very, very compliant. So now we're going to take exactly the same sample. In fact, I think it's the same sample. Not exactly the same, but this very sample. And we're going to do the same experiment, but at a much lower strain rate of 9 times 10 to the minus 4 per second. And you can see it buckles to the right because of that crossover point. So now we're playing with the relaxation time against the experimental time frame on these polymer systems. This also manifests itself in the stress relaxation, if we hold it for 10 seconds, it curls up after a stress relaxation experiment. And if we hold it for 1 hour, it can curl by a lot more. And so I put this for Dick here because we have shape memory effect in these. So when we make a flower out of these and then lock in the shape, everybody loves the tulip shape for some reason. So when we program the shape at 90 degrees, and then we're going to relax it. So here's the calcium, and here's the aluminum. And so this is at room temperature now, right? And so we're just placing them on a glass slide, and you can see that the aluminum one blooms right away, and then the calcium one takes a lot longer to bloom. And so they both return to their original program shape. So there's shape memory effect in these. Okay, I think this is one last thing I want to show. Okay, this is a battery. So I wanted to show you a little bit of the multifunctionality of these. So this stimulus can be made different. So in this case, the stimulus is electrochemical. And so it's in fact a battery, and you're looking at it from the top. And when we lithiate it, you can see what's going to happen when we lithiate it. It forms this pattern. So I'm a musician. To me, they look like violins. They are sinusoidal patterns that form as a result of lithiation. So instead of the silicon fracturing, the beams now bend to accommodate the triaxial stresses of the lithium being inserted. And so what we observed is that sometimes when these nodes counter-rotate, it creates mode 1 buckling. But when they co-rotate, it creates mode 2 buckling. So it's almost like we're forming a domain or a distribution of domains. And so the FEM simulations show very much the presence of both types of modes of buckling. The color here represents the lithium concentration of the lithium diffusing into it radially. And so my student Xiaoxing noticed that when you change the lithiation rate, in fact, when you speed it up, the number of domains increases and the domain size shrinks. And so I don't know if you're familiar with the icing model, but it looks like the icing model, which basically involves a coupling coefficient between adjacent nodes, can really explain this. And so Xiaoxing started using this to program defects into a structure. And so this is a battery, and we hit a pattern into it. You guys don't know what this pattern is yet. And what I'm going to do is simply lithiate this battery. Okay, you don't know what's hidden in there. We might have programmed something in there. Maybe we didn't. And all we're going to do is now just lithiate this structure. This is a very, very legitimate battery. And hopefully you can see that the image that emerged in there has a lot of resemblance to my little logo. Okay, so that's the end. So then, very relevant here. Why did you show us this? So what? Showed us some, hopefully I was able to show you some interesting thought-provoking videos and some data. And I would argue that if you're careful about controlling 3 very critical things, one of them is the atomic layer microstructure, atomic level microstructure of your material. Is it amorphous? Is it nanocrystalline? What is the atomic level microstructure? The second one is the size effect. Every class of materials exhibits a size effect, and you need to know where that transition length scale is, because only then does it become interesting. And then the third one, of course, is the type of architecture you're making, like some of the beautiful structures that you guys make here. What are you making it for? Do you want more surface area? Do you want more stiffness? What is it that you're going after? You can create entirely new classes of materials with uncoupled properties, which we hadn't been able to do before. And the reason why you might want to do this is so that we'll live in the world with no hearing aids, because we can just write the cochlea bone and put it directly in your ear someday. Your iPhone 83 won't need to charge it for about a year. We can make much better batteries now, right? Did you know that helium is actually a precious resource? So if vacuum is lighter than air, so if we can make balloons out of nanolattices that are not porous, we can evacuate it, right, and use just vacuum and stop using helium. Almost relevant for the season. The Christmas ornaments won't shatter. This is my favorite example, so brownies, right? So our latest, greatest pursuit is chocolate nanolattices, which are 100% taste, 99.9% air, and 0.01% calories. And with that, this is my group. This is our outing to the Joshua Tree National Park. So we just went on a group retreat. And a big thank you to all of you and to all my funding sources. And sorry for being a little late. Thank you.
Thank you for the great talk. Very